Welcome back to ECE 340, test day -1. Is that true? Well, I mean -2, but the next time we meet, the next class time is exam number 1. Hopefully that doesn't surprise you or come as a surprise to you. There is a review session scheduled for this evening or this afternoon at 5 p.m. in room ECE 530. If you're interested, I will try to record that and post the notes if you are unable to meet that time, but that seemed to be the time with the most scratches next to it when you were voting. Homework 2 is due today. It looks like I'm collecting a pretty good stack, and if you don't turn it in here, you can turn it in physically to a mailbox in the ECE building if that is easier for you. That's basically the only place to turn it in after. You could turn it in at the review session if you want and really confuse me. No, that should be fine. The goals today, as I want to simply communicate, sometimes I just forget this. I think it's been posted indirectly on the cover sheets of some of those practice exams. You hopefully know what the process is. It's not that complicated, but I just want to make sure everyone's on the same page. We'll talk a little bit more about BIBO stability today. We really didn't get to cover that much, and we will actually go into more types of stability for exam number 2, and you'll be able to then distinguish between the different types of stability, but I want you to at least be aware or understand this bounded input, bounded output stability so that you can perform the calculations on exam number 1. This is really an input-output stability concept. It's dealing with the system or a transfer function between a particular input and a particular output, and you're looking at the poles of that transfer function to determine the bounded input, bounded output stability. You could then draw a line underneath that. That's the end of material for exam 1. I kept wondering why people were asking if convolution was going to be on exam 1, but there are some problems on some of the practice exams, so now I can kind of understand the concern, but convolution will not be on this exam this semester. It will obviously be on subsequent exams. And hopefully we'll get through or get started with an intuitive or a qualitative understanding of convolution and get into some examples of convolution. But we will probably go through that somewhat quickly. I'm assuming you've seen it before, maybe 2 or 3 times, and so I don't want to keep hitting you with convolution. I'm going to assume you can do that. And I may post some more videos on that we won't have discussed in class. The process for exam 1, it's closed notes and closed book, with the exception of you do get 1 sheet of note paper, and that's 8.5 inches by 11 inches, front and back, and we will just add to this as the semester progresses. With each exam, you'll get 1 more sheet. By the time the final exam rolls around, you'll have 4 sheets of notes if you're trying to plan how you're going to create your note sheets prior to the exam. Calculators, I'm allowing any calculator. Just don't expect to use a computer. I'm not going to probably have MATLAB questions anyway, but yes, if you had a computer, you could probably check your work a lot of different ways, but with some of the calculators floating around these days, it's essentially a computer anyway, but you have to know how to use it, and we'll try to help you with that as we move through in terms of using MATLAB and calculators, and obviously something to write with. The main thing there is don't necessarily erase anything. If you think you're in error, just cross it out and ask for another sheet of paper. Hopefully I'll bring some blank sheets if you're running out of room on the paper. sometimes your first approach might actually be a correct approach, and in the heat of the battle you kind of get yourself confused. Partial fraction expansion, we really aren't worried so much about those coefficients for this exam. I just want you to be able to find the roots. So if you can do the quadratic formula and find roots, that's what you need for this exam. I want you to be able to find the structure of a partial fraction expansion, but just as a precursor to the more detailed analysis, if you do have the good fortune of having a TI-89, I created some YouTube videos for how to do partial fraction expansion with real roots, complex roots, when those transfer functions are actually proper transfer functions, meaning the numerator degree is the same order as the denominator degree, and you can use your calculator to do that long division process for you prior to having it also find the partial fraction coefficients. That's just information for your use for later, but I mention it occasionally to students, and I thought, okay, I probably need to remind everyone that that is available. And if you're on YouTube, you can go and watch these videos at the ECE site for the U of A. Questions on exam 1 or any material that we've had so far? Let's then talk about bounded input, bounded output stability a little bit more. Since you did so well on the previous quiz, let me give you another one. A quiz is different from the exam, but here's another quiz. Here is the S-plane with the real horizontal axis and the vertical imaginary axis. And let's say that somebody gives you a couple of x's. The x's correspond to what? Poles. So now we have two poles, no finite zeros. Somebody might say, oh, you have two infinite zeros. That's okay, but we're really more worried about finite poles and zeros. Poles and zeros that are in the finite or are bounded in this S-dimensional this S-plane picture. Is this system, if I just gave you that, and that's all I gave you, can you tell me, is it BIBO stable? It's not, is it? Because these, if I've drawn them accurately, those are right on the imaginary axis, and the poles, all the poles have to be strictly in the left half plane. This is not in, or I should say not, BIBO stable. On the exam then, if you find or are given a transfer function, you'll need to find the roots of the denominator polynomial and see, are all of the real parts of those roots negative? Are all of those poles in the left half plane? If they are, your system is bounded input, bounded output stable. In this particular case, we could create a transfer function. We could say, well, we have a transfer function with two poles. One of those poles is on the upper half of the imaginary axis, and that gives rise to this factor s minus j2. The other one is in the negative vertical half of the S-plane. And I haven't said anything about the numerator, but let's just assume that its numerical value is 1. We didn't have any open circles, so we know we don't have a polynomial of s other than an s to the 0. So this is a constant term, and I didn't scale that other than just to make it a 1. If we now multiply this out, then we end up with an s squared plus, well, maybe if I do FOIL, why don't I just go ahead and do FOIL since I've got it all here. I have minus j2s plus J2S, and there's where it then goes away. We have minus a J squared. J squared is minus 1 times a 2 squared, so we're left with 4. And now our H of S, this system that has 2 poles on the imaginary axis, is now this system that has purely imaginary poles. H of S is 1 over S squared plus 4. In fact, you could think of this as an oscillator, meaning if I kick this system, if I hit this system, what's going to happen? It's going to just sit there and shake and shake and shake. Because the real part of those poles is 0, we do not have any e to the, let's say, minus 1t or e to the plus 1t. We have nothing decaying or growing with those poles. It's all with this oscillating term, and the oscillating frequency is 2. Now, if this system, which it is not, bounded input, bounded output, stable, can you give me an input, a bounded input, that would cause this system to have an unbounded output? Any suggestions on how I could select a bounded input that would produce an unbounded output? Okay, so this has a frequency of oscillation, this system of 2, doesn't it? If we just hit this system with an impulse or a step, it would have just shaking at 2. But if we enhance, or if we keep encouraging that system to oscillate at the same frequency that it naturally wants to oscillate at, if we hit it with a sine or cosine of that same frequency where the frequency is 2, now it's going to build. The response will build as a function of time. A bounded input that will yield an unbounded output is then x of t equal to sine of 2t. That's a bounded input, has an amplitude of 1. It's bouncing between plus and minus 1, but it's at the same frequency as this system naturally likes to shake. And so you're encouraging that system to move as it naturally likes to move, and now that will give rise to this unbounded question. So this is the question was, is this sine of 2t the inverse Laplace transform of 1 over s squared plus 2 squared? It's related to that. It's a multiple of that. If we had a 2 over s squared plus 2, then it would be exactly this sine of 2t. It's just a scaling factor away. So yes, the inverse Laplace transform of something with that denominator would either be a sine or a cosine, depending on what the numerator has. In this case, the numerator does not contain an s, so we know it's not a cosine. We know it's actually a sine. And now it just depends on what that numerator was, how big that amplitude of the sine was. Question? Correct. So when I'm saying a bounded input, I'm meaning its amplitude. So the question was bounded referring to what? Amplitude or time? It's unbounded in extent, isn't it? Its region of non-zero value is infinite. because it goes from, well, depending, a lot of times we start things at 0 time and then it goes on forever. The amplitude is what I'm referring to when I say it's bounded. The amplitude of this x of t, in this case, has a magnitude of 1. It's bounded. We could have put in x of t equal 10 to the 6th sine of 2t. That's still bounded. It's big, but it's bounded. Is that okay? And you could see this if you simply said, well, I still don't quite see what's going on, but we know the relationship between the output and the input. It's just the system h times its transfer function times the Laplace transform of the input. The h was just this s squared plus 2 squared. And if we Laplace transform this sine of 2t, that's this 2 over s squared plus 4, or s squared plus 2 squared. The key concept here is that we now have a denominator term that's squared. Meaning if I gave you, let's say, an output that had a Laplace transform 1 over s, what would that be in the time domain? That's a step, isn't it? It's constant with 1. If I gave you an output in the Laplace domain, y of s equal to 1 over s squared, what's that? That has that t, doesn't it? That's a ramp. So that s squared, every time you increase the power in the denominator for that factor, you're incrementing your t in the coefficient of your expression. And here, what this results in is if you go through the algebra, you will end up with a t times a sine or a cosine. In this case, if I've done the algebra right, which I'm not sure I would trust my algebra, and this is maybe then scaled by minus 1/4, but this t is coming about because of this squaring in the Laplace transform of capital Y of s. And that then is causing this cosine to just go unbounded as a function of time. And our input x of t was this sine of 2t, just as a reminder. The magnitude of that, that's what we're saying is bounded. That was less than, well, or equal to 1 upside down a t, or for all t. So this was a bounded input. But it gave rise to an unbounded output. Yes? Where did the minus 1/4 come from? That was, you've seen the cartoon where a professor is up deriving something on the board and it's just a mess of derivation, and then they just say some magic happens and he writes it down, the answer. Well, there's some analysis going on to get that minus 1/4. You have to now go back to whatever tables you like or whatever way you like to inverse Laplace transform, and you will find that when you have a factor, this s, let's say in this case, s minus j2 quantity squared, that's going to give rise to terms that will eventually end up giving you this minus 1/4. But the t in front of the cosine is due to the quantity s squared plus 4 quantity squared. That squaring in the y of s gives us the t, and that's the critical thing. I'm not so worried maybe about this scaling. I can see no matter what that is, whether it was plus 5, minus 7, it's going to give me an unbounded output. So I didn't show you where that came from, but you can now go home and derive that and correct me if that's not right. But this T is correct. Okay, and that's the critical thing. Now what we will do post exam number 1 is we will start looking at different kinds of stability. We now, I hope, are pretty comfortable with BIBO stability. And this is actually what I've been calling input-output stability. And we will now subsequently, in future material, talk about asymptotic, or, yeah, let me just quit there. So let me say asymptotic stability, where this is more of an internal stability concept. Meaning you might have, and I always sort of start sniffing, because if you have a system that you can't tell is unstable, but it's internally unstable, it's probably burning up. Your electronics are going to saturate, something's going to happen. You'll be able to tell that it's not stable eventually, but theoretically, you could have something that is stable from an input-output perspective and not stable internally. Are we okay with BIBO stability? Do I need to show any more? I had another example, but I think we're good to go on